Hi everyone! In this video, we are going to be looking at ionic compound names and figuring out the formulas. So it's going to be going in the opposite direction of what we did in the last video, where we were looking at formulas and figuring out names. We will be using the same method that we talked about in class in order to do this, and you might remember that that method was called identify, simplify, switch. So on this slide, I'll just go into a little bit more detail about each of these steps, and then we'll get some practice with some example problems on the next slide. So the first part is to identify, and when we say identify, what we're talking about is that for each ionic compound, there are going to be two components. There's going to be a cation and an anion. And in the identify step, you want to figure out what the chemical symbol is for the cation and the anion. And the only tricky part is that the cation and or the anion could either be a monoatomic ion or a monoatomic element ion from the periodic table, or it could be a polyatomic ion from this chart on the back of the periodic table. And so the first thing you'll have to do is to figure out where you should be looking in order to find out the symbol or the formula. Should you be looking at the periodic table, or should you be looking at this polyatomic ion chart? For the cation, the positively charged part of the compound, it's almost always going to be straight from the periodic table. It's almost always going to be monoatomic. And the way that you can, the only real exception is going to be ammonium, which you can see right here. So NH4, that's kind of like the one common polyatomic cation. But for the most part, you're going to find your cations in the first, one of the first two groups or columns on the periodic table, sometimes also in this third group over here, or 13th group over here. So for the most part, we're going to say the cation is going to come, the symbol is going to come from the periodic table. For the anion, the way that you should decide whether you'll look at the periodic table or whether you'll look at the polyatomic ion table is to look at the ending of the name. If it ends in "ide", that's a really good clue that it's going to be from the periodic table, and it's just going to be an element, a monoatomic ion. If it ends in something other than "ide", then that's almost a surefire clue that it's going to be a polyatomic ion. And in that case, you'll have to look at this polyatomic ion table in order to figure out what formula you should be using. So that's the identify step. The simplify step just means that you should look at the numbers, or you should look at the charges for your cation and your anion. And you will have a plus charge for the cation and a minus charge for the anion. And what you want to do is simplify those numbers so that you get the simplest possible ratio between them. So if your cation was +2 and your anion was -2, then that really is simplified down as a 1-to-1 ratio. Or if you have something like a +4 and a -2, then that simplifies down to a 2-to-1 ratio. So just simplifying the charges down to the simplest ratio that you can between the two of them. And then finally, the last step is to switch. So in this step, what we're doing is we're taking the ratio number, the simplified charge that we figured out in the previous step, and we're taking the number for the cation and making it a subscript for the anion, and vice versa. We're taking the simplified charge for the anion and making it a subscript for the cation. There are two catches here. One, if the subscript or the simplified charge is a 1, then we don't write anything. So if there's no subscript present, the implication is that it's a 1. But if it's a 1, we don't actually write it. The second thing that I want to mention just briefly is that it's important to know that the actual charges of the ions themselves aren't being swapped around. So it's not like the anion is actually giving its negative charge to the cation in some way, or the other way around. It's just a trick for figuring out the subscripts that you'll need to use for these problems. Okay, so let's go ahead and get some practice with some problems. So this first problem is sodium acetate. So the first thing that we'll do is we'll look at the cation, which is sodium. Hopefully sodium sounds familiar to you guys at this point, and you'll know that you can find it on the periodic table. It's right here in the first column. And so elements in this first group have one valence electron, and they are going to lose that valence electron in order to become stable. So they're going to be forming cations that have a +1 charge. So we'll write the chemical symbol for sodium, which is Na, and its charge, which is +1. And then the second part of the name is acetate. And if you look at the end here, acetate, it doesn't end in IDE. So that's a good clue that we should look at the polyatomic ion table to figure out what we should be writing for acetate. And if you look over at that table, you'll see the very first entry in this first column is acetate. And so we know that the symbol that we need to write is C2H3O2. And acetate is in this -1 column, and so that means it has a -1 charge. So at this point, we have identified both the anion, sodium, and the cation, acetate, and we've given a charge to both of them. Our next step would be to simplify, but since we have +1 and -1, we can't simplify it any further. It's already as simple as it's going to get. And then the other thing to note is that since we're dealing with only ones, we have +1 and -1, but the numbers for both are 1, there's not actually anything that we're going to write for this. So we totally disregard these ones because we're not going to write them down. So instead, we just write our formula as it stands here. So NaC2H3O2. And that's it. That's the formula for sodium acetate. Okay, so let's move on to a different one. So this is sodium fluoride instead. So we're going to have the exact same cation. It's still going to be Na, it's still going to be +1. But now when we look at the name for the anion section, we can see that this ending is an IDE ending. And so that means that we should be looking at the periodic table to figure out the symbol. And fluoride is going to correspond to fluorine as the actual element that it's coming from. And so we'll write an F over here for fluorine. And in this, you can see that it's in this 17th group, so it's going to have 7 valence electrons. And in order for fluorine to become stable, it's going to, excuse me, it's going to become a -1 ion, since it's going to gain 1 electron, and therefore it'll have a -1 charge. So fluorine has a +1 charge. So now we've done our identification. We have Na and we have F. We have a charge for both, plus and minus, or oh, sorry, this should read -1, plus and -1 respectively. And so again, we can't simplify it because it's already 1-to-1, and we're not going to actually write any subscripts because we're only dealing with ones. So our formula will just be NaF. Okay, so let's do something slightly more complicated or challenging. So this next one, it says iron, and then in parentheses, we have the Roman numeral 3, chloride. And when we were talking about transition metals in our naming video, I said that it was always kind of a pain when you would look up a symbol and find that it was a transition metal because that meant you have to do Roman numerals. But when you're finding the formula for an ionic compound, it's actually really nice when you get one that has to do with a transition metal because it tells you right in the name what the charge for iron is. So all you have to do is find the symbol for iron on the periodic table. So if we're looking for iron, we can find it right here. So the symbol for iron is Fe. And then instead of having to figure out the ion what the charge is going to be based on the row or the positioning or the column or the positioning, instead it's right in the name. It says iron and then 3. So we know that this iron is going to be +3 because it says it right there in the name. And then for the anion, we'll look at the ending, and we have an IDE ending here. So that tells us that we should go to the periodic table, and chloride is going to correspond to chlorine. So our symbol will be Cl. And again, it's in that group where it's going to have 7 valence electrons. So just like fluorine, it's going to form -1 as its charge. Okay, so we've done the identification. So let's see if we can simplify. We have a 3 and a 1, so it doesn't get much more simple than that. We are going to disregard the 1 because we don't care about the 1. And we'll do this last step, which we can actually do now, which is the switch. So nothing's going to happen with the 1 because we don't like 1 subscripts, but we do have this 3. So we are going to switch that with the take that 3 and associate it with the chloride. So our final formula will be FeCl3. And so this switching, or this like swapping and dropping method, where like you can imagine a little 1 right here, but we just don't actually write it in the final formula. That's one way to think about it. Another way to think about it is that our iron has a +3 charge. And so in order to balance it out, in order to get a final charge that's neutral, we need to have 3 chlorines. Because if you have an Fe and it's a +3, and each chlorine is just 1 minus, then in order for all of our charges to balance out, like to do like the charge accounting, we need 3 total chlorines. So this 3 subscript is really just saying that we need 3 chlorines to neutralize, to make a no charge, to balance out the +3 on the iron. So whichever way of thinking about that makes the most sense to you, it's a totally valid way to write the formula. Okay, so let's keep going. We've got another sodium, which has got sodium all over. So again, it's going to be Na+1 for the same reasons that we said before. And then if we look at the ending here on carbonate, we can see that it's not an IDE ending, it's an 8. So we should look in our table to find carbonate. And it is the first entry on, oops, no. It's the first entry on our -2 column. So this is carbonate right here. So we can write that. It's CO3 and it has a -2 charge. So for sodium carbonate, again, we cannot simplify because we've got a 1:2 ratio, which is as simple as it will become. But we do need to do some switching. So we're going to take this 2 and put it down with the sodium, and we don't care about the 1. So our final formula is Na2CO3. And that's it for sodium carbonate. Okay, this next example is another transition metal name. So we've got copper sulfate. So the first thing to do will be to find copper on the periodic table. And we can see that it is right here, copper. And so Cu is the symbol that we want for copper. And this time we see a 2 in parentheses. So we know that this copper ion is going to have a +2 charge. And again, we can look at the ending for sulfate and see that it ends in ATE, not IDE. So that means that we should look for sulfate in our polyatomic ion table. And sulfate is right here, SO4 2-. So we can write that SO4 -2. And this time, we do have a simplification that we can do. +2 and -2 is really the same thing as saying +2 and -1. A 2-to-2 ratio is the same thing as a 1-to-1 ratio, for our purposes at least. I think in general. And so we can do that simplification. And now that we only have 1s, it's a +1 and a -1, we don't need to do any subscripts because we're just dealing with 1s. So even if you originally had a charge that was not a 1, these were 2s, once you simplify them, if they turn into 1s, then you're still not going to write the subscript. So our final formula will just be CuSO4, and that's it. Okay, we've got 3 more examples, and let's take a look at what we'll be dealing with here. Okay, so magnesium is right here on the periodic table in that second group, and that means that magnesium has 2 valence electrons. It's going to donate or lose both of them to form a cation of +2. So let's start by writing Mg +2. And then hydroxide is, I think, the one exception the one notable exception to my IDE rule. So even though it ends in IDE, there's no element that corresponds to. So even like hydrogen would be hydride, helium isn't involved in any reactions. So even though it's hydroxide, it actually is a polyatomic ion. It's like the one polyatomic ion that ends in IDE, or at least the one common one. So hydroxide is right here on our polyatomic ion table. So we do have to write OH as our formula. And it's in the -1 column, so we'll write -1 right there. So we've got both the cation and the anion identified, magnesium and hydroxide. We've got their charges. We cannot simplify them because it's 2 to 1, which is as simple as it will get. And then we do have to do some swapping and dropping. So nothing is happening with this 1, but with this 2, we need to associate it with the hydroxide. So this is where it gets a little tricky. The way that we're going to write this is, I'm going to move over to the left here. It's going to be Mg, and there's no subscript for that. And then it's OH2, but because we have 2 and it's a polyatomic ion, we're going to have to use parentheses. Anytime you use a subscript with a polyatomic ion that isn't 1, because you wouldn't be using a subscript in general if it was 1, you need to put parentheses around the entire polyatomic ion. And the reason for this is that if we wrote it like this, if we wrote MgOH2, what that says is that we have 1 magnesium, 1 oxygen, and 2 hydrogens. But the whole point of these polyatomic ions is that they come as a package deal. The O and the H are always going to be together. So whatever, if we're getting more than 1 H, it needs to come with the associated O. It's like with, I don't know, like certain people, you always see them with somebody else. Like they always go together as a pair. So this OH, they're always together. So if we're going to be multiplying them, they need to be together. And we show that in chemistry by putting a parentheses around them. So whenever you're using a subscript with a polyatomic ion, always put the polyatomic ion in parentheses. That's the rule. We'll get more practice with these next 2 problems with that rule. Okay, so barium nitrate is our next example. Barium is also in the second group, but it's a little further down. So barium, since it's in that second column, it's also going to have a +2 charge. And the nitrate ends in ATE, so that means we need to find it on our polyatomic ion chart. And it is right here. So nitrate is NO3, and it's -1. And if we look at these charges, +2, -1, we cannot simplify, but we do need to put the 2 down with the nitrate, and we don't care about the 1. So when we're writing this one, it'll be barium, Ba. There's no subscript with that because it would have just been the 1. And then for the nitrate, we want to get 2 of them. We're putting the 2 with the nitrate. So that means that we need to use parentheses and put the NO3 in parentheses. And then we can write 2 for the subscript. Okay, one more example, lithium sulfate. So lithium is right here. It's in that first column. So Li +1. And then sulfate is going to be on our polyatomic ion table. It's actually one that we used already. It's this one. So sulfate is SO4, and it's a -2. Okay, so again, no simplification, but we do need to do a swap. We're going to take this 2 and put it with the lithium. So it's going to be Li subscript 2. And for elements, or for a monoatomic ion, you don't need to do any parentheses, because in this case, lithium's hanging out all by itself. It's not attached to any other atom. So a subscript of 2 lithiums means 2 lithiums, and that's totally fine. So you only need the parentheses for the polyatomic ions. And SO4, there's just 1. So we don't even need parentheses because it's just a single SO4 group, I guess. So just 1 unit of SO4. So our final formula is Li2SO4. Okay, I hope that this video is helpful for going from a ionic compound name to a formula, and I will see you all soon.